Somewhere in the universe, right now, there is a place where time itself stops moving. Not slows down. Stops. Completely. If you fell toward it, your last second would stretch out forever. An outside observer would watch you freeze in place, fading into darkness, never quite vanishing. But from your own perspective, something far stranger happens. You cross the line in an instant. And once you do, there is no version of physics, no amount of thrust, no miracle of engineering that can bring you back. This is not science fiction. This is a black hole. And in 2022, scientists pointed a network of telescopes the size of Earth itself at one, and captured something that should not have been possible to see. What they found didn't just confirm Einstein's century-old predictions. It also pointed straight at a question physicists have been terrified to answer for 50 years. A question about information, about memory, about whether the universe is allowed to forget. Stick with me. By the end of this, you'll understand why some of the smartest people on the planet believe black holes might be the most important objects in all of physics. Not because of what they destroy, but because of what they might be hiding. Let's start simple. A black hole is not a hole. That name is misleading. There is no tunnel, no portal, no hollow space waiting to swallow you. A black hole is something far stranger. It's matter, crushed by gravity until it stops being matter in any way we understand. Here's how it happens. A massive star, many times the size of our sun, burns through its nuclear fuel over millions of years. Fusion in its core pushes outward. Gravity pulls inward. For most of the star's life, these two forces are in perfect balance. Then the fuel runs out. Without fusion pushing back, gravity wins. Instantly, the star's core collapses in on itself in less than a second. What used to span thousands of kilometers gets crushed down to a single point. Physicists call this point a singularity. It has no size, zero volume, but it can still contain the mass of several suns. Around this singularity, gravity becomes so extreme that it warps space itself into a sphere. This sphere has a name, the event horizon. It's not a physical wall, it's a boundary. A line in space where the escape velocity needed to get out exceeds the speed of light. And since nothing can travel faster than light, nothing that crosses this line can ever come back. Not light, not radiation, not information. That's the part that should terrify you. Imagine you're in a spacecraft, approaching a black hole from a safe distance. From where you sit, everything looks normal. Stars, darkness, the faint outline of the event horizon ahead, lit only by the glowing disk of superheated gas spiraling into it. You decide to get closer. As you approach, something strange starts happening to your perception of time. Light from your ship, watched by your friend back on Earth, starts arriving slower and slower. To them, you appear to be moving in slow motion. Your voice deepens. Your clock seems to tick slower and slower. This is gravitational time dilation. The closer you get to the event horizon, the slower time appears to move from the outside. But here's the part that breaks people's brains. From your perspective, inside the ship, nothing feels unusual at all. Your clock ticks normally. Your heartbeat is steady. All time for you is doing exactly what it always does. You cross the event horizon and feel nothing special happen. But your friend back on Earth? They never see you cross it. As far as their instruments can tell, you slow down, dim, and fade into the background glow, approaching the horizon forever, but never quite touching it. Two different realities. Both true. Both impossible to reconcile from where you're standing. This isn't a flaw in the map. It's a feature of how gravity bends space-time itself. Now let's talk about what actually happens to your body. As you fall toward a black hole, gravity doesn't pull on you evenly. Your feet, closer to the singularity, get pulled harder than your head. The difference might be small at first, but as you fall closer, it grows exponentially. Eventually, the gravitational pull on your feet becomes so much stronger than the pull on your head that your body starts to stretch. Not metaphorically, literally. Your body elongates into a long, thin strand, like a piece of spaghetti being pulled apart by two hands. Scientists actually call this process spaghettification. It's not a joke name made up for YouTube. It's the real, accepted term used in astrophysics for a stellar mass black hole. This happens long before you reach the event horizon. You'd be torn apart by tidal forces well outside the point of no return. But for a supermassive black hole, the kind found at the center of galaxies, something stranger happens. The gravitational gradient is gentler. You could, theoretically, cross the event horizon completely intact, with no sensation of stretching at all. You'd cross into the one place in the universe that nothing escapes from. And you wouldn't even know it happened until it was already too late to matter. Here's where things stop being a horror story and start becoming one of the deepest unsolved problems in physics. In the 1970s, physicist Stephen Hawking made a discovery that should have been impossible. He showed that black holes aren't perfectly black. They radiate. Slowly, almost imperceptibly, they leak particles into space, a phenomenon now called Hawking radiation. This means black holes lose mass over time. Given enough time, longer than the current age of the universe by an absurd margin, a black hole will fully evaporate. It will disappear. And this is where the paradox begins. Quantum mechanics has a rule that physicists treat almost like a religious commandment. Information cannot be destroyed. Whatever falls into a system, the precise quantum details of every particle, every interaction, must in principle be recoverable. The universe, according to quantum theory, never truly forgets. But if a black hole evaporates completely, what happens to all the information that fell into it? Every book, every atom, every photon that crossed the event horizon, all of it, according to Hawking's original calculations, simply vanishes when the black hole finishes evaporating. No way to recover it. No trace left behind. This directly contradicts quantum mechanics. One of these two pillars of modern physics has to be wrong. Either information really can be destroyed, breaking quantum theory, or something about our understanding of black holes is fundamentally incomplete. Physicists call this the black hole information paradox. And for nearly 50 years, it has had some of the greatest minds in history at a complete standstill. In recent years, researchers have proposed an idea so strange, it sounds like science fiction. Maybe information doesn't get destroyed. Maybe it gets encoded onto the event horizon itself, smeared across its surface like a hologram. This is called the holographic principle, and it suggests something deeply unsettling. It suggests that everything that falls into a black hole, every detail of every object, might be preserved as a kind of two-dimensional projection on the boundary of the horizon. The three-dimensional reality we experience might, in some deep mathematical sense, be a projection of information stored on a lower dimensional surface. Some physicists take this even further. They argue that our entire universe might work the same way, that the three dimensions we move through every day could be a holographic projection of information encoded on some distant boundary we can't perceive. It sounds absurd, but the mathematics behind it has held up under intense scrutiny for over 2 decades. It's one of the most successful ideas in modern theoretical physics, even though nobody has proven it describes our actual universe. In 2019, the Event Horizon Telescope captured the first ever direct image of a black hole, the supermassive black hole at the center of galaxy M87. In 2022, they did it again, this time imaging Sagittarius, a star, the black hole at the center of our own Milky Way. These weren't just pretty pictures. They were direct tests of Einstein's predictions, made nearly a century after he wrote them down on paper, with no way to ever check them. Every measurement matched. Every prediction held. We are now, for the first time in human history, able to directly observe the objects that might hold the answer to one of physics' oldest questions. There's something almost poetic about a black hole. It's the place in the universe where our best theories, the ones that predict the orbit of every planet and the behavior of every particle, completely fall apart. It's a boundary not just in space, but in human understanding itself. And maybe that's exactly why it matters so much. Because every great leap in physics has come from exactly this kind of contradiction. A place where two things we know to be true cannot both be true at the same time. The people working on the information paradox today aren't just solving a puzzle about black holes. They're searching for a deeper theory of reality itself, one that can finally unite gravity and quantum mechanics into a single coherent picture of the universe. We don't know what they'll find, but somewhere out there, in the darkness at the center of a galaxy, light is bending around an object that may be quietly holding the answer. Waiting, patient, indifferent to whether we ever figure it out. Maybe that's the real lesson of the black hole. Not that some things are lost forever, but that even at the edge of the unknown, the universe is still keeping score. Every mystery leaves a door open somewhere. We just keep looking for the ones nobody's walked through yet. If you want more stories like this, you know what to do.